Dear academics, ladies and gentlemen, we often seek a single universal solution for complex problems. In mathematics, one powerful technique is the Wiener-Hopf method. It was developed in the 1930s by Norbert Wiener and Eberhard Hopf to solve an obscure but crucial class of integral equations. But the question is, can it solve any problem? The answer is definitive no. The Wiener-Hopf method is not just a general purpose algorithm. It is a specialized analytical tool. Its fundamental mechanism involves transforming the integral equation using the Fourier transform and then performing an ingenious step called Wiener-Hopf factorization. This splits the complex transform function into two parts. One analytic in the upper complex plane and one in the lower. Its power is immense in solving mixed boundary value problems, situations where a physical quantity is specified differently on adjacent boundaries. This makes it indispensable in areas like diffraction theory, calculating how waves, light, sound, electromagnetic bend around the edge of a plate or a wedge, acoustics and electromagnetics, analyzing wave propagation in structures like waveguides or cracks, green theory, which is my favorite, and finance, solving certain probabilistic or stochastic processes. The technique's major limitation is that it only works when the problem can be reduced to a convolution integral over a semi-infinite range. As soon as the geometry becomes finite, say a plate of finite length instead of infinite half plane, the problem becomes much harder. Generalized Riemann-Hilbert problem, often requiring numerical or entirely different analytical methods, like the method of moments or the finite element method. Current research focuses on pushing these boundaries. Scientists are tackling problems that are close to being Wiener-Hopf solvable. Generalized and matrix Wiener-Hopf problems, extending the factorization to matrix kernels, which arise in analyzing coupled systems or anisotropic materials. Approximate factorization, developing methods to find approximate solutions when exact factorization is impossible. Numerical implementation, integrating the analytical rigor of Wiener-Hopf with efficient numerical schemes to solve larger, more realistic engineering scenarios. A PhD dissertation in this domain might focus on deriving a new analytical solution for challenging novel geometry, for example, the diffraction from a material with a specific type of surface impedance. The goal is often to find a closed-form solution, an exact formula, which is the gold standard of analytical work. Postdoctoral research often transitions into applied multidisciplinary work. A postdoc might use the fundamental analytical insights of Wiener-Hopf to validate or improve computational solvers. They might analyze complex real-world devices such as photonic crystals or new metamaterial structures. Using the technique as a benchmark for accuracy and efficiency, often leading to publications in high-impact journals in mathematical physics or engineering. So while the Wiener-Hopf technique is not a universal solvent, its elegance and analytical power make it one of the most celebrated specialized tools in the applied mathematician's toolkit. It remains a dynamic and relevant area of research, continually being adapted to solve the wave propagation mysteries of tomorrow. Thank you, and see you next video. And please write your commentaries if you really like queen theory or Wiener-Hopf method technique. See you next time. With you, Alexandra Chudinova, the founder of the Foundation for Academics.